So here we have the XOR function, and we're trying to build the neural network. There is this input data, then there is this hidden data, and there is output data, output layer, right? Now what you can do is you can step node by node or layer by layer or complete full run and see how the forward propagation and the backward propagation is happening. What this does is it takes the inputs on what is the learning rate, what number of hidden layers, and what are the number of nodes per layer. Then it builds the network, and as you build, you can step through the whole network. Suppose I want to build network by network, so node by node. So first one, I am going from input 1 to hidden 1 1. Then hidden 1 2. Then hidden 1 3. Then after hidden 1 2 3 is done, I am going to output. Now what will happen? You will have to, this is the forward propagation. After that what will happen? You have to back propagate the error. What is the error? Minus 0.426, that's error. It is propagated to third one, it is propagated to second one, it is propagated to first one. So now you see the weights have been updated. These weights have been updated based on back propagation. Now these layers again you go back and propagate the previous layers. You see each of these layers now will be updated. The weights will be updated and come back to the original. Again go forward, go backward, go forward, go backward, and then when you run a full so it has reached up to, it's expected 1, but it's reaching up to 0.9387. See what it's doing? It's doing forward propagation, it's backward propagation. Forward propagation, backward propagation. So I want you to try this. This is an example of where you can go node by node, or you can go layer by layer, or you can go example by example. Example by example means 0 1 will go to 1, 1 1 will go to 0, 1 0 will go to 1, and 1 1 will go to 0. So let's try with example. So what it's saying is, I'm doing for, it's a mini batch size equal to 1. So that means it's doing for each example at one step. So it's very, very slow. See what it's doing? First 1 0, then 0 1, 0 0, then 1 1, then 1 1. So for each example it's doing the forward, backward. Again trying one more example, one more example. So like that it's doing for each row forward and backward. Then again take the next row, doing the backward and forward. So ultimately, idea is if you have 1 0, what should be the value here? 1, right? It's reaching close to that. But are you getting exactly 1? So you stop when threshold is within what you specify. For what? So here you can specify the threshold. When I did the design, I said tolerance is 0.1. Suppose I said 0.01. Then it will go on till the tolerance will be 0.98, 0.97, that level. It is gone to 0.97. So because I have specified much smaller tolerance limit as compared to earlier, I had specified 0.1, it stopped at 0.9, as it reached, it stopped. So depending upon what is the delta at which you want to stop, this backward propagation, forward propagation step will stop. Again, as I said, this one can be done in, for example, like what we call as mini batch size equal to 1, or you can do it as batch, or you can do it as all in one and complete till you reach a threshold. But what is the underlying step that is happening? Depending on the structure of the network and the activation function, you do the forward propagation, which is take sigma Wi, run activation function, get the output. Next layer you perform the same thing, you go on to the output layer. Then at the output layer you see that there is an error between expected value, which is 1, and what you got, that's the delta. You propagate it, and in doing that what you do, you update the weights. Then you get the output value here, propagate it backward to the next layer, update the weights till you reach here. Then you take the next example, run it, and till you reach stability. What is the point for conversion? Either you specify a fixed number of steps, say 10,000 steps I want to do, means 10,000 examples I have done, or I can specify tolerance limit within 0.01, something when I reach for all the 4 outputs, I am okay to stop. So both ways to stop. One is non-deterministic based, I don't know when it's going to converge, I will only base it on the tolerance. Another way is saying that I will fix number of steps, I will do some 1,000 steps, I am done. Got it? So what is the underlying principle, what is going on here? The underlying principle here is that we are working on 2 basic technologies. One is error propagation. What is error propagation? Error propagation means you take an error at the output node, propagate it to the previous layer using the notion of gradient descent. Depending on the activation function, the update of delta W will be governed by the formula which is governing the activation function there. So what will you do? You take the delta W and put it into action. You update the weight. Like that, you update the weight of the previous layer. You keep on doing that till you reach a stable state. What is a stable state? Either in terms of fixed number of steps or in terms of tolerance. And this is something which is not rocket science. It's something you have to keep experimenting. I won't say that this is the perfect number of steps which is going to make you converge. Sometimes you may converge much faster than what the number of specified. Sometimes you may not even converge. If there is no actual pattern, neural network may not converge also. That's another risk. Think about it. Deep learning may not always guarantee you convergence to a pattern. If it's not existing, pattern does not exist, this can keep on going into an infinite loop. So it's sometimes a good idea to put a threshold. How many number of steps you want to do. So given this, what is the parameters which are in your control? If you want to experiment, you have input-output combinations. Let's say you have, these are the inputs in terms of images and these are the output classes you have. What is the things you have in control in terms of designing the network? Number of layers, number of nodes, activation function. Sometimes there is also control on the different variants of the backpropagation. What happens is, while I have said that gradient descent is the most common way of optimizing, there are other optimization techniques which are there in the history of neural networks. So what will happen is, you will typically have something known as a set of predefined optimizers. Some of them could be based on idea of gradient descent. Some of them could be based on very custom network based structure called like ADA. So what in the next class we will do is, we will look at some of the optimizers. But before that, I have told the TA to get you a lab on just experimenting with structures, different structures for a standard problem called MNIST character recognition. What is MNIST character recognition? MNIST is a collection of fonts of numbers. It's a library created by a group of people who have created some 10,000 characters and benchmark them. This is 0, this is 1, this is 2, this is 4, this is 9. So that you can take as base, and on the basis of that, you can create a neural network based classifier, which is multi-layer perceptron classifier. But what will be in your hand will be the structure of the network. How many nodes in what? You can try with multiple structures of the network. Then you can also try with different optimizers which are present there. And you can see how the precision or the accuracy varies depending upon the structure of the network you propose. You propose two layers with two. When you say proposed structure, it's about hidden layers. Input and output are always compulsory. But what you can vary is number of hidden layers and what is the number of nodes in each hidden layer. So you have to specify in form of 10 in the first node, 20 in second node, 10 in third node, maybe 3 layers. So that's something which is in your control. So what you can do is, in programming that, you can change the structure of the neural network and see how the accuracy of the problem changes depending upon the structure. You understood? So it's not going to be like you have the flexibility too much in terms of defining fine-grained network level activation functions, because typically what happens is these networks, once you define an activation function, it's standard across all the layers and all the nodes. So it's not so much flexible that you change every node level thing. But what is important for you is that sometimes fewer layers will perform better than having a lot more layers. So it's not going to add incrementally. Sometimes 2 layers of 5 nodes or 10 nodes will be better than having 3 or 4 layers with multiple nodes. But you have to do the experiment. Just like in case of say decision tree. Did you always say that so many layers of the tree is better than other? You have to keep on trying, right? You have to keep trying different topologies of the tree. What are the parameters for the tree? Depth of the tree. What kind of function you will do to split the tree? Is it based on entropy or is it based on Gini? Then we say what kind of leaves I want to add the leaf node, or what is the minimum balancing fraction. Those are the parameters for you to govern the decision tree problem. In here, in the neural network case, the parameters which are in your control will be the structure of the network, the optimizer function, which is basically what I'm saying is the back propagation. What is the function which you take from delta and apply it to update the weights?